Okay, we're now going to look at some basic derivative rules of exponential functions and logs. And so what I have here is a graph of y equals e to the x, which is an exponential function. Remember, e is the natural base. I'll give you, e is an irrational number, and let me write it down here. We didn't really talk about this. One thing about the textbook we're using at the moment here is it doesn't really stress exponential functions for whatever reason. I think part of the reason is exponential functions are known as transcendental functions, meaning you don't calculate them with the regular algebraic rules. In the past they would use tables. Now we have calculators to do exponential functions, and they do talk about it later on in the class in a chapter on transcendental functions. But the thing is, trig functions are also known as transcendental functions, and they do highlight trig functions. They do stress that. They have a chapter in that beginning in the first chapter of the book. They have a section on trig functions. So we didn't really talk about exponential functions and logarithmic functions. So just a quick review here, that this y equals e to the x is this exponential function. So as you go off to negative infinity here, these are negative exponents that are getting bigger and bigger. So you get 1 over e to some really large number, and so this thing approaches the axis asymptotically. Okay, now when you go through the y-axis, when x is equal to 0, e to the 0 is 1. So any exponential function is going to pass through 0, 1, and then it's going to shoot off to infinity. And it's going to grow very, very large, so as these exponents get bigger and bigger. So this thing grows very, very rapidly. Okay, so the natural base is this irrational number, and it shows up when you do like continuous compounding, like in a bank account. You can compound, annually. You can compound the interest quarterly, monthly, daily, but you could compound it every instant. And when you do that, this irrational number shows up. That's known as the natural base. And when things grow continuously, so like populations will grow continuously, things decay continuously, so like radiometric dating, you end up getting the number e in your expression to really model that sort of growth or decay. Okay, and so what we're going to find out is that this is also a very important function in calculus, because we're going to see in a minute that this is the only function that the derivative of the function is equal to itself, which is a very unique property about y equals e to the x. So this is just the inverse of that function. So if I rotate this around the line y equals x, right, kind of twist it, if I held these two corners and twisted it around, I would get this. So this here, this asymptote is like where this is going off to 0, because this negative x-axis becomes the negative y-axis, and then so it's going off to 0, and then here it goes through this point, 1, 0, right where this goes through 0, 1, and then this thing grows very, very slowly. Well, that represents this growing really fast, very quickly. This grows very, very slowly, and so it just really grows very slowly, and as you go on it grows more and more slowly, but it does keep growing. Okay, so the domain is actually negative infinity. I'll write these down: negative infinity to infinity to infinity. You can put in any number as an exponent and you don't get a problem. The range here though is, it'll never be 0. Okay, it approaches asymptotically, so it's 0 to infinity. Okay, oops, this is the range. Sorry, the range. Okay, well this just switches them around, right? So here the domain is 0 to infinity, so you can't put in 0 in a log. You can't put in a negative number in a log. Okay? But you can get 0 and negative numbers out of the log because the range here is negative infinity to infinity. So the log goes down to negative infinity. It'll keep rising up to positive infinity, even though it does it very, very slowly. Okay? So, excuse me. So let's think about the derivative here. If you notice this asymptote, the slope of the tangent lines here are very, very close to 0, right? And then it goes up here to 1. Here at 1, the slope of the tangent line looks like y equals x, and it actually is y equals x. So so there at 0, the slope of the tangent line is 1, and then after that, so let me write this. Let me do this. This tangent line has a slope very close to 0. Here, the slope of the tangent line is 1, and then when you get off here, these slopes start increasing more and more rapidly as you go up. So basically, over here, slopes are close to 0. Going through here, the slope is 1. Over here, slopes increase very, very quickly. Well, it sounds like I'm describing the slope. When I describe the slopes, I'm describing the function here, right? And I am doing that. And so the derivative here for e to the x is actually e to the x. So like I said earlier, the derivative of e to the x is equal to itself. I think this is the only function that's equal to its own derivative. And so that's a very unique property about e to the x. Okay? Very special property. Okay, well that would be nice if this here was equal to itself, but it's not. And we're going to see what it is equal to here in a minute. So let's just think about the behavior. As I get close to 0 here, right, this thing is going to negative, it's going to, I'm sorry, the slopes are going to positive. So as I get close to 0, look at the slopes of these lines, right? Like here, the slope is equal to 1. I'm sorry, at 1, the slope is equal to 1, yes. And then here, the slopes are getting closer and closer to 0. But here, the slopes are positive, and they're getting closer and closer to positive infinity. So let me try to draw a little graph here of what's happening. So as you're getting closer to 0, these slopes are going off to positive infinity. They're getting steeper and steeper and steeper. So the slopes are going to positive infinity. Here at 1, the slope is actually equal to 1. And then here, the slopes are getting closer and closer to 0, right? This thing is just leveling off. Even though it never completely levels off, and it continues to grow, they get closer and closer to 0. So it really looks like this. It looks like y is equal to 1 over x. For this portion, at least for this part of the domain. Okay, it doesn't include this portion, but the domain is just 0 to infinity. And that's actually what it's equal to. So the derivative of d of x of the natural log of x is equal to 1 over x. So these are the main two derivatives for exponential functions. As it turns out, they're the only ones you need because you can rewrite functions in terms of e to the, I'm sorry, you can write any exponential function in terms of e to the x, or any log in terms of the natural log. If you remember, there was only those two buttons. It actually has a common log and a natural log button, but you can use those two buttons to find any other logs. Okay, but I am going to, let me actually give a rule here for for other exponential functions. So if you have a to the x, where a is any base here, but a needs to be positive, because you can't take like a half a power of a negative number. That'd be taking the square root of a negative number, right? It ends up that this derivative is the natural log of a times a to the x. So it's the natural log of whatever the base is times a to the x. And this here, the derivative d dx of the natural, I'm sorry, of log base a to the x. So this is some other base, log base a to the x. This is not as common here, but it's going to be equal to 1 over the natural log of a, whatever the base is, times x. Okay, so you can think of it as being, you can think of these as being proportional. So this is equal to itself. This is proportional to itself, and the constant of proportionality is just the natural log of a. Okay, here you can think of this as being 1 times the natural log of a times 1 over x, if you wanted to. So this is kind of equal. This is kind of equal to that, but there's a constant. It's proportional to that, but there's a constant of proportionality that's 1 over natural log of a. Okay, so these aren't as common. These are the ones that we usually end up using, and the relationship between these are related to like change of base formulas and changing an exponential function like this to e to the x and all of that. I'm not going to get into that. We're just going to use these four. These are going to be our 4 shortcut rules. And let's just do a couple of these then. Look at a couple of these. So if I wanted to take the derivative of 3e to the x using the constant multiple rule, this is just going to be the constant times the derivative of e to the x. And e to the x is equal to itself, so it's just 3e to the x. Okay. Now this one here, if I take the derivative of 10 to the x, this is going to equal the natural log of 10 times 10 to the x. Okay, minus 10 e to the x. This is just that constant times the derivative of e to the x. So that's what it would look like there. Okay, so this one here, f prime of x, the derivative of natural log is just 1 over x, and then this would just be plus 2 to the x. And what's interesting here is you got this logarithm. Well, now everything's just algebraic, okay? And so this kind of transcendental function went away and gave you an algebraic function. And you could combine this over a common denominator or whatever if you wanted to. Okay, well this one here, I have 3 log base 2 of x minus cosine x. So the derivative for this one would be, we're going to have 3, and then log base 2 of x would be like natural log of 2 times x. So it'd be, this is like, just taking the derivative of this would be 1 over natural log of 2 times x, but you have the constant multiple of 3, so I put it on top. And then the derivative of cosine is the opposite of sine, so the opposite of sine, that opposite will make that a plus sine x, and I would get that. So what I wanted to do then is say, now there's still things that we can't do, okay? Like I couldn't do something as simple as y equals e to the negative x, right? I wouldn't be able to do that. I couldn't do, and it's because of the negative inside there. I couldn't do y equals something like x squared e to the x. I couldn't do that. Okay? I couldn't do something like y equals even x times the natural log of x. Okay? It's because this is the product of two functions. That's the product of two functions. Or I should have done something like natural log of x over x. This is the quotient of two functions. So all of these things. This one is a function inside another one. So I couldn't do something like this. If I had like y equals e to the square root of x. Okay, this is a function inside. That's a composition of two functions. I couldn't do something like sine of x squared plus 1, because here I'm putting one function inside another function. Or I couldn't do y equals even something as simple as the natural log of x plus 1, technically, because this is another function inside a function. Okay, there's a lot of stuff I can't do, but you can see the problem here is when I have like ones like these, if I have a composition of two functions, can't do it. If I have a product of two functions or a quotient of two functions, I can't do it. So what we're going to do is we're going to learn in the next videos 3 really important rules. The product rule will allow you to do ones like this. Product rule, where you have the product of two functions. We're going to learn a quotient rule, where you can find the derivative of the quotient of two functions. And then we will have something called the chain rule. And in the chain rule, you'll be able to find the composition of two or more functions. Okay? And so that's what we have coming up.